So what I'm going to do right now is I'm going to do kind of a crash course on titrations, and what Luke just said, or the question that Luke asked was, how do we know whether or not we're supposed to do titration or an ice problem or whatever else? So here's the key, and here's the secret. All titration problems are just a form of a buffer problem. So with a buffer, do you remember how buffers always took place in 2 steps? Step number 1 was take care of the big dog, and step number 2 was do an equilibrium problem. And typically that involved using Henderson Hasselbalch. Well, titration is almost exactly the same thing. So in order to demonstrate this, let's take an example of a problem, shall we? So let's do, and I'm going to do the problem that was in the textbook just to kind of help you with that. So we're going to use the weak acid being titrated by a strong base, and we're going to use. Let me just find this for you. So if you guys want to look in your textbook with me, let's go to page 731. 731. Okay. So what we're doing in this case, and you want to write this as our starting point at the top. Let's write, we have 50 milliliters of 0.1 molar acetic acid.
Wait, do you want 15?
I'm sorry, 50, not 15.
50?
50.
Like that? Or
yeah. 50.0. So 50.
Oh, okay.
50.0 milliliters of 0.1 molar acetic acid with a Ka of 1.8 times 10 to the negative 5. And it's going to be titrated with 0.10 molar NaOH.
With how much?
0.1 molar NaOH. And can you, on the far right-hand side of the board, can you make a graph? That's your left. So yeah, right side. Keep it right there. Can you make like a Cartesian graph? So make a big L space there. We're going to work off of that. That should be about right size-wise. Okay, so with a titration, there are 5 points that we always want to include on a titration graph, sometimes 6. First is before we add any big dog. Second is somewhere between the start and the half equivalence point. Third is the equivalence point or half equivalence point. Fourth is someplace is the equivalence point, and fifth is someplace after the equivalence point. Now that may not make a whole lot of difference to you, but what the equivalence point is when we actually have completely used up whatever we're titrating. So remember, in a buffer, we'd have, go with me. In a buffer, we'd have an acid and a conjugate base both sitting there, and when we drop the big dog in, depending whether or not the big dog was a strong acid or a strong base, it would go after one of those two, and we do an equation written in moles. Well, we do the same thing here, except in this case here, can you put your finger on the HAC, HAC? Okay, we only have an acid. We don't have a conjugate base. So when we throw in NaOH, put your finger on the NaOH, please. What we're really throwing in is OH minus. Agree? That OH minus is a strong base, and so our equation, just like we've done in a previous problem, is the OH is going to attack the HAC. Now I'm going to get to that in a minute, because the question that Luke asks is, how do we know whether we're doing a titration or an ice problem? Well, before we start a titration, and titration is just a fancy way of saying a neutralization. And in this case, do you see how we have an acid, HAC, or acetic acid, and we're going to titrate it with a strong base, OH minus. But how do we know when we do an ice problem, when we do a titration problem? Well, in every single titration problem, they always are going to want to know what is the pH before we do the titration. So if we don't have a titration going on, can you put your hand and cover the titrated with portion? Just cover that whole portion right there. So if I just gave you the upper part, 50 milliliters of 0.1 molar HAC, and I gave you the Ka, couldn't you figure out what the pH was that by using doing an ice problem?
Yes.
Yeah. So whenever we start a titration, our very first step is to do an ice problem. So let's set up HAC throwing it into water. And Mary Catherine, can you guys unmute your video, please? You and Brian.
Into water or with OH?
Yep. Thank you. We always throw something into water when we're doing a Ka.
Okay.
I would 100% suggest that you guys write this down as you're going through, because even if you're watching it, it's kind of helpful to have you go through the mental process of doing it. Okay. Now, don't we know the initial amount, the initial concentration of the hack? And in this Luke is what we're addressing. All we have, and step number one in every titration is they want to know what is the pH before we add any of the big dogs. So we're just going to do an ice problem, because all we have. Can you write ICE down the side? Because all we have is 0.1 molar of the hack and 0 and 0 of everything else. Oh, I love how you put a line through there. Minus X plus X plus X. Again, brilliant. And then 0.1 molar minus X and X and X. So can you write the law of mass action? Ka is equal to, and actually put the values in. H3O plus.
Wait, okay, you want me to just...
I want you to actually just put the, just so we get in the habit of it. The square brackets of H3O plus times square brackets of AC minus all over the square brackets of hack. Okay. Now we can plug in the actual values here. And in almost all these problems, I'm going to let you do the 5% rule. 5% rule says that we can get rid of that X. And that's equal to 1.8 times 10 to the negative 5.
Anyone have?
Okay. Can someone solve for X there? And then take...
Yeah, this will work.
By the way, just so you're aware here, isn't the X value equal to both H3O plus and AC minus? Isn't it equal to both of those things? But we don't care about the AC minus because they're not asking us to figure out anything about the AC minus. They're asking us to figure out the pH, so we want to figure out the H plus concentration. Why did that turn on?
Is that what you got?
Mom, can you give me an ibuprofen, please? Since we're a smaller group here, I need all you guys kind of working feverishly to make sure we get through this as quickly as possible. So what we're going to do is this. I want us to actually draw these positions on the graph. So on the top, the 0 mark, I want you to make a 7, and then a 14. Let's stretch the y-axis a little bit farther out so we have a little more differentiation. And I want all of you drawing the graph, because the graph portion of this, they are graphophiles on the AP board. They love seeing graphing. And on the bottom in a second, we're going to do graphs. Let's do 50 milliliters at a pop. So spread it out a little bit more. So actually, you should probably be okay like that. So then about 3 inches from the 0, just put your pen down about right there. Put 50. And then the same distance apart, put 100. And then 150. And then 200. And on the bottom, I want you to write milliliters of OH. So ml of OH. And on the y-axis, we're going to write pH. Okay, so the reason we're bothering to do the first step is that we want to know what the pH is of the acid before we start titrating with OH minus. So in this case, then we discovered it was 2. I think that's 5.7, but I don't have a hard time reading it. So I want you to make a kind of a big circle there where the 2.57 is.
Right there?
Yeah, I can't really see it, but I'm assuming everyone else can, yeah? Good. So that's the only time, and this is still in a very convoluted answer to your question, that's the only time, Luke, that we actually do an ice problem from the very start. Because take a look at the next quantity they give us. So I'm looking in the textbook. So to the right of where you've done that, so right to the right of where it says up above, yeah. So we're actually going to do like A is going to, or B is going to be So A is no NaOH. Yeah, so A, which we just did there, so that's no NaOH. B is going to be 10.0 milliliters of 0.1 molar NaOH.
Of how many molar?
0.1 molar, 0.1 molar. Okay, so really quickly, now we have the big dog and we have the original acid that we're dropping it into. So every single time we have big dog, we're always going to do the stoichiometry equation, and it's going to look exactly like we did with buffers. So here, by the way, NaOH, I want you to get used to immediately getting rid of the Na+. You realize the Na+ is nothing there, right? So we're going to write OH minus plus hack and a one-way arrow. Okay. Now, do you guys realize that all of our titrations have to be done in moles or millimoles, right?
Yes.
So since they give us milliliters, and I refuse to allow you guys to do liters because that's just so much extra work, isn't 10.0 times 0.1, isn't that 1 millimole? And if you look at our hack, didn't we start with 50 milliliters of 0.1? Isn't that 5 millimoles? Now, here's the thing you need to be aware of, and let's do this. Can you write ICF? Because I just want to differentiate, because here we're going to have an initial amount, then we're going to have a change, and then we're going to have the final amount. Now, here's what you need to be aware of with or let me remind you of what happens when we're dealing with a strong. It will completely use itself up or use the thing that it's attacking up. And here, if we have 1 millimole of the strong base and 5 millimoles of the acid, won't the 1 millimole of OH minus completely use itself up? So can't we go minus 1 millimole from that, won't it minus 1 millimole from that, and won't it plus 1 millimole on the other side? So won't we have 0, 4 millimoles, and 1 millimole? Are you all okay with that? Now I want to point out something to you here. Do you see how now we have 4 millimoles of the HAC and 1 millimole of the AC minus?
Yes.
Isn't that an acid-base conjugate pair? So in reality, we could do an ice problem, but we're not going to do that anymore. We're going to do exactly what she's doing. We're going to do pH equals pKa plus a log of AC minus over Ha. HAC. Now, before we plug anything in here, do you realize that AC minus and the HAC minus, those are concentrations in molarity, right?
Yes.
So what we need to do is we need to take our 4 millimoles, and now we're going to divide it by the total volume.
Which was 50.
50 plus 10, so we're going to have 60. Does everyone see that? Just to start us here, if you actually solve for the pH on that, it's going to end up being 4.14.
Okay.
So
4.14.
4.14. So when we drop in the big dog, which is a strong base, and we're only putting in 10 milliliters, so you're going to have to go over. So divide the 0 to the 50 into like 5 little marks.
Okay.
So initially, we're going to shoot right up. And that makes sense because we have an acid by itself, and now all of a sudden we're adding a strong base to it. Yeah?
Yeah.
Now, the next really important point on any graph. So what we've done is this. We've gotten 2 of the 5 points we need. Point number 1 is initial before we add any of the strong base. Point number 2 is some point in between that and the half equivalence point. And point 3 is the half equivalence point. So let's go C. And C, we're going to add in 25 milliliters of the 0.1 molar NaOH. Now, just so you're aware, we can actually keep on using that the big dog equation written above if you don't want to write it over and over again. But see how instead of 1 millimole, and 5 millimoles, do you realize we're going to have, so let's just keep on using that space. Keep the 5 millimoles because that's never going to change as a starting point. Right? So we're going to have 2.5 millimoles and 5 millimoles. Now, if you can math, which you guys all can, do you realize if I react 2.5 millimoles with 5 millimoles, I'm going to use up exactly half of the millimoles? So we're halfway to completely neutralizing it. So we call that the half equivalence point. Now, watch, and this is kind of cool. And in both these cases, I'm going to have to divide by the overall volume, which in this case now is going to be 50, 75. But let me show you something that's really cool. Write the pH equals pKa. Write the Henderson-Assenbach equation again.
Where? Yes.
Yeah, it's AC minus. This to actually make it AC, since we're AC minus and HAC, just because we are using acetic acid. So would you agree with me that both the AC minus and the HAC are the same exact concentration?
Yeah.
So if they're the same concentration, wouldn't that be equal to log of 1? Does everyone see that?
Total volume. So you had 25 milliliters and plus the original 50.
Divide by the the total volume is the original plus the thing. Now hold on before you write anything here. Stop for just a second. Get rid of the negative log for just a second. Would you agree with me that if that log of 1 is equal to 0, wouldn't the pH be equal to pKa? Can you write that down and write pH is equal to pKa, and then do the at sign, like the little at symbol, at half equivalence point. So 1/2 equivalence point. So you know what's really cool is you can actually do the math. You can do the math and solve everything out, or you can just say this. If you're ever doing like a math problem and you see that it's 25 millimoles or 2.5 millimoles is being added, you can say pH equals pKa at the half equivalence point, and that can be all your math. So then you can just go negative log of the Ka is equal to your pH. Are you all with me here? So at the half equivalence point, and how do we know it's a half equivalence point? Because you see how we've used up 2.5. So put your finger on the 5 millimoles of the HAC to begin with. If we use up 2.5 millimoles of that, haven't we used up exactly half of the millimoles, Mary Catherine? You see that? I'm waiting on you, or ask a question if I need to clarify. You can unmute if you need to.
You say.
Wait, 5?
So we start off with 5 millimoles. Can you put your finger on the 5 millimoles? And we reacted 2.5 millimoles of the OH minus. When we do that, it's going to use up 2.5 millimoles of the HAC. So we're going to end up with half of what we originally started.
Okay.
If the whole point of a titration is to use up everything exactly, that's what we call the equivalence point. So the half equivalence point is when we used up exactly half of what we started with. See how we're left with 2.5 millimoles after we've used up 2.5 millimoles?
Yes.
And that's enough for us to make the statement in red. pH is equal to pKa at the half equivalence point. I do want you, however, to actually do the math on that. So pH is equal to pK is what?
Wait.
Okay. Okay. The 5 and 50 0.1 that's how we got that. So we got this from C. We got this C. We got milliliters from 25 milliliters 1.1 molar. So that's how we got then we want to neutralize all of OH minus. That's why we subtracted 0.25. And then from that, we only got half of HAC. It says the half.
Okay, why are you dividing by 75?
Oh, because in order to plug it back into the Henderson-Hasselbalch,
Molarity. I mean, we have millimoles and then we have milliliters, and so you take 25 milliliters and 50 milliliters, and that's where we got 75. And so when we divide by the liters, we get the molarity, and that's how we put the molarity into.
and if you notice here how millimoles and milliliters, the milli cancels out, so then we end up with moles per liter.
Okay, and then
Anything else?
the at 1/2, it's like 1/2 of the red.
Oh.
Okay, so since they're both concentration, they're both 2.5 divided by 75, then
That's
this
one.
and so all equals 0. So we just take that out totally. And so you can always just say that pH equals pK at the half equivalence point. Just make it.
Okay.
So you don't have to do any of the work we just showed. They're going to assume that you understand that if we're at the half equivalence point, pH is equal to pKa. So you can literally just go negative log of the Ka and know what your pH is.
Cool.
And the actual value, if you actually plug that in this case, is 4.74. So at the 50 mark, it's going to be 4.74. You're exactly at the 50 mark right now. No. You see 50? We're at 50. So draw your, I'm so sorry. Sorry, my bad. We're at 25, my bad. So let's do this. Let's switch this out here because I want to make it bigger. Let's make the 50 mark 25 milliliters. It's going to make our graph a little bit awkward, but actually let's do this. Let's make each one, like each mark 10, 20, 30, 40, 50. So where the 100 is, that's going to be our 50 mark. And then let's make it 5 even parts.
Wait, so 10, 20.
That's probably a little bit wide. So wherever the 100 was before, where was the 100 before? That was the 100?
Yeah.
Okay, so where the 100 was, right there, let's make that 50. And then let's go 10, 20, 30, 40 in between. Yeah, that's fine. I was thinking of actually between the 0 and the 50, erase the 25 in the middle, and just make 4 marks in between, so it goes 10, 20, 30, 40.
Oh. Okay.
And then we can do the same thing between 50 and 100. Okay, and so I'm assuming here if we have that, yeah, you're gonna have to slide over just a little bit, I think, for the 10 milliliter mark. The 10 milliliter mark, I think we said it was 4.14. And at the 25 milliliter mark, it's going to only be 4.74. So see how it's kind of curving over to the side?
Yeah.
Now, at the equivalence point, so let's jump to the equivalence point. Actually, they don't want you to jump to the equivalence point. They actually do 40 milliliters as well, but I'm not going to do that. Let's jump right to the equivalence point. So let's go D is going to be 50 milliliters of 0.1 molars added.
50 milliliters of 0.1. 50.
Yep. So see, in this case, we have 5 millimoles of 5 millimoles, which means we're going to have 0 and 0, and all we're going to have left at the end is the 5 millimoles of AC minus. Now, going back to what Luke asked at the very beginning, at the equivalence point, you're going to have to do an ice problem again. Because take a look here. Normally, when we do Henderson-Hasselbalch, equation if we had both an acid and a conjugate base, but didn't the big dog completely use up exactly our acid? So all we have left is the AC minus. So what do we do with AC minus when in doubt? Throw in the water, right? Good. Very pleased to hear that. Okay. And now we're back into ice territory again.
That's 0.05 molar, right?
I didn't know it was the amount 100 milliliters.
It was 100.
Okay, so that goes 0.05 mil. Can you do ICE on the side there? Does everyone see how we are forced to do an ice problem here because all we have left at equilibrium is just the AC minus, which she circled. Okay, let's ice this problem. Hey, Mom. Yeah, can you bring me an elevation bar, please?
And then it's KB now, right? Wait, it's 1.4 times 10. Or 1.0
times 10 to the negative 14.
Does anyone have that?
Can you hear me now?
What?
Can you hear me now? Okay. Sorry. So I was talking, you guys didn't hear me. I guess I muted myself. So I'm glad you caught on this because we had a Ka to start with, right? So we had to switch to Kb. And once we have the Kb, which I guess someone's going to give you, which I guess I could give you as well.
What?
Kb is 5.6 times 10 to the negative 10. Okay. Can't we just write that? Let's draw the law of mass action and solve it. Okay, so OH minus concentration in this case is 9.1 times 10 to the, actually try again, it's 5.3 times 10 to the negative 6.
Yeah, what he said. Why are we even doing calculations?
Okay,
That's OH, we don't like OH, do we?
No.
we just do the negative log of it and then minus 1.
I love that.
Does anyone have it?
Hold on.
Cody, don't give up.
So when you do that, that's pH is 8.72. Well, hold on.
Wait, the POH or the pH?
The POH, I don't have because I didn't solve that way.
Okay.
5.27.
Ha! Okay, so that's the pH.
POH.
And then, okay, yeah.
You subtract that from 14 to get your pH. I love that you caught this, by the way, Kirsten, because two things that need to be caught in this. One, we have a base right now, right? So we have to switch our Ka to Kb, which I'm delighted you did. And then two, when we're solving for X, we're no longer solving for H+. We're solving for OH minus, which means that if we want to get the pH, we then have to go from OH back to pH land. And there's more than one way you can do that. Can you write on the left-hand side here the two quick equations? Can you write pH plus POH equals 14? And can you write H plus concentration times OH minus concentration equals 1.0 times 10 to the negative 14? So we could have done one of two things. We could have taken the OH minus concentration and used the bottom equation to figure out the H plus, which is what I did in the textbook, and then take the negative log of the H plus. Or we could have just taken the negative log of the OH minus, which I like better. Take the negative log of OH minus and once you get that, subtract from 14, which I kind of like as a better move. Either way, isn't our pH 8.72 at the equivalence point? So let's put that on the graph. So kind of extrapolate up, and you're going to be past the 7 altogether. You're at the 50 mark right now.
I'm at 50?
50, yeah.
Oh, yeah, okay. And then 8.7.
So you're at 8.72, so you're almost at 9.
Yeah.
Okay. Now, what's kind of interesting is the way we're going to actually draw the graph is you're going to draw a line that's going to go up, and then when you see you're going to draw a curve between the second dot and the third dot. It's going to be a curved line that's going to straighten out almost completely flat when you hit the third dot. Shooting up, and then you're going to curve, and your curve almost. I want to curve it though a little bit.
What do you mean? Like,
So it's still going to be like it's going to curve.
that?
More of a yes, but more of a if you were to draw between those 2 points, kind of a gentle curve.
Oh, okay. So,
Yeah. Okay, and then what you're gonna do is you're gonna almost keep on going straight, and then shoot straight up. Go a little bit longer on the bottom, because what happens when you get to the close to the equivalence point, the pH just shoots almost vertically up perfectly. So we're gonna go right to there. So we're gonna come to a couple of important points in just a second, but there's one more point we have to do. So we have to do 1 point after we finished here. So let's go 75 milliliters being added in.
do you want me to erase all of this?
Well, you're gonna have to use the same equation there, so you don't have.
Not that?
Yeah, you can still do that. Yeah, that's fine. So we're just gonna do 75 milliliters this time. So if you notice the 4 points we've plotted so far, 1 point at the initial, 1 point half somewhere between the initial and the half equivalence point, and now we're doing some point afterwards. And I want to point out something to you how you're actually gonna like these a lot.
Is that right? Like, subtract.
Yes, absolutely. Why? Everyone, look at what you just did. Tell me why.
You cut out. Did he?
He crashed or something.
No.
Greg!
All right, we have to do this problem.
We gotta do it alone.
Yeah.
Okay.
So it's
I'm lost.
-5, -5 plus 5. All right, 2.5 remaining.
Okay, so I just.
Oh, you're back.
Evidently, I accidentally put the screen down, and it. Yeah. So evidently, I'm still broadcasting. You guys are still broadcasting. So that's good. Okay. So I love what she did there because. Can everyone see why she only used 5 millimoles of the OH minus up? Because we only had 5 millimoles of hack that were to be used up, right? So everyone see that, because this is a big deal. Because if you try and subtract 7.5, you're going to end up with a negative amount of the hack, and there's no such thing. You can't produce 7.5 millimoles when only 5 millimoles of the hack will respond. So now watch, and this is an incredibly big deal. Would you agree with me that there's AC minus? Can you put your finger on AC minus? Okay, isn't that a base?
Yeah.
But it's a really weak base. And if we were to do an ice problem like we did before, that ice problem is going to spit out a little bit of OH minus. The last problem, didn't it spit out something like, I want to say 5.3 times 10 to the negative 6. That's how much OH it spit out. 5.3 times 10 to the negative 6 molar. Do you understand how small 5.3 times 10 to the negative 6 molar is? So if we were trying to figure out which contributes OH minuses, we have pure OH minus. Can you put your finger on OH? Yeah. We have 2.5 mil on the OH up above. Just put up there. Your finger on the OH. Yeah. We have 25. Is it 2.5 or 25? 2.5 millimoles. 2.5 millimoles of pure OH minus. So in order to figure out the pH, we're not going to worry about the AC minus, because AC minus is going to produce almost nothing OH minus wise. So all we're going to do is have to convert that to molarity, and then we can take the negative log of that and figure out our POH.
Is that 115? Or am I off? 125 or 115? 125.
And you're going to like problems where you've overrun the buffer, because it makes your problem really, really simple. All you have to do is divide by the volume, and take the negative log. Now be careful here, because isn't this the negative log of the OH minus?
Yes.
So what do you end up with?
Come on, Cody.
1.69 or 1.70.
1 point what?
70.
1.70.
And that's going to give you, subtract from 14, will that give you a pH of
13 point.
12.30?
Oh yeah.
Come on, Kurt. Just call him math.
Make sure you put 12.30 because we're using two significant figures, and then the decimals only count after the decimal, after the thing. So 12.30. So let's go to the 75 milliliter mark.
So what milliliter mark? The 75?
75, and let's go all the way up to 12.30. Wonderful. So now we're going to do another, so you're going to go almost completely straight until you're almost at that dot, and then you're going to curve it over. Now curve it.
Like that?
Yep. Okay. Now, let me point out a couple things here that are incredibly important about this graph. So first of all, can we put little arrows and go half equivalence point to the dot that's at the 25? Just go the third dot. Third dot, like underneath it, put a little arrow underneath it, going towards it, and say half equivalence point, so half equiv point. And then the fourth dot, put equiv point.
Wait, so why does it change?
Okay, so when you look at this real quick, I want you to notice two things here. And you can put a little, why don't we put a dash down below and write 25 milliliters, because just to show, like in red or in black, whatever, a different color, where the actual half equivalence point is. Isn't it 25 milliliters?
Yeah.
And then the equivalence point, it's exactly at 50 milliliters, right? So will you take a note here? Would you agree, all of you, that the equivalence point is exactly double the amount of stuff added as the half equivalence point? This may not seem like that enormous a piece of information, but it is, because if you know how much you've added to get to your equivalence point, you can always divide it by 2 to get to your half. Or if I tell you, hey, it took 25 milliliters to get to my half equivalence point, I know how many milliliters I have to get to my 50 to get my equivalence point. Any questions so far?
Wait, do you want to know how that happened? Right? Okay, so.
Well, can you answer her question or repeat her question so people listening can follow? What did she ask?
He asked why the pOH was 1.70.
Okay.
Do you want me to answer?
Yeah, go ahead and answer.
Oh, okay. So you read? Want me to explain it or no?
I want you to explain it because it's a good question.
That means it's acidic. Well, yeah, but like you can have a pH of 12.3. It's just like it's a basic equation. No. So you got it? Okay.
Okay, so what the question was, and I just want to reiterate this. In order, when we overrun the buffer, can you put your finger on the 2.5 millimoles?
Wait, where do I put it?
On the 2.5 millimoles on the E for that, right up above, right there. So that 2.5 millimoles is what's left over of just strong base. And in order to figure out the pH of that, we have to convert that into volume. And the way we did that is by dividing by the 125 milliliters, I think it was.
Yeah.
And that gave us our volume of, I can't read the number there, but
0.02.
0.02. And we take the negative log of that, we get the pOH, then subtract the pOH, 1.70 from 14. That gives us our pH. Now, there's a couple of things I want to point out to you here. Do you guys realize the half equivalence point, pH is equal to pKa?
Yes.
It would be different because the AC minus the OH minus it'd be independent of the OH minus being added in there. Because if you did the pH, Luke's question is, if we were to try and figure out the pH of the AC minus, but here's the problem, we can't, because the AC minus doesn't have a big fat OH minus sitting on top of it. So the AC minus can't do its normal equilibrium. Yeah, if there was no OH minus left over, we could do what we did at the at the equivalence point and just go AC minus, throw it into water. But here's the thing. AC minus's little world has been crushed because there's 2.5 millimoles of OH minus sitting there. So you can't ask the question, what would the pH of the AC minus be? Because it's irrelevant because there's so much OH minus already in the equation, it doesn't get a chance to. In fact, do me a favor, write the AC minus equation in there, AC minus plus water. Goes to H2O or OH minus plus the AC minus, yeah. Okay, do me a favor here. Write 5 millimole, or write 5 millimoles of that, and then write 2.5 millimoles on top of the OH minus, underneath the OH minus. Write 0 for the hack. So do you realize if we were doing a weak acid problem with AC minus, wouldn't we be trying to solve for the amount of OH minus that it produces? But don't we have a ton of OH minus already in the solution? So what we do is we go minus X, and then when we go plus X on the other side, and would you acknowledge that 2.5 millimoles plus X, that X that's being produced is going to be so minimal compared to the 2.5 millimoles that the 2.5 millimoles is essentially going to be the only thing that we see. In fact, when we do the math on the X, someone did it in the previous problem, and the previous problem wasn't it 1 point something times 10 to the negative 8 was our X value? If you take 2.5 and add 1.0 times 10 to the negative 8, how much does that change my 2.5? Do you understand? So in a very long answer to your question, Luke, the reason we don't care about the AC minus is because the amount of OH minuses that the AC minus is going to produce are so tiny compared to the OH minus we actually already have. There's no point in figuring out the pH for it. It'll be exactly the same pH overall as what the OH minus gives us. Okay. All right. Now, let me tell you 2 other points. One of the things they often ask you is, what are the major species at each point? So can we start off at the first dot? First dot. And on the side there, what is the only thing we have at the first dot?
pH or like no.
Which acid of our acids or bases? Don't we only have HAC? Don't we only have acetic acid at the starting point?
Yeah.
So can you write HAC next to it? So I want to walk you through so you can see what things are at what point. Okay. At the third dot, don't we have exactly the same amount of HAC and AC? So you can say HAC equals AC. At the second dot, don't we have both HAC and AC? At the second dot, not the fourth. Yeah. Second dot. But wouldn't we have more HAC than we do AC? A little greater than symbol. How about that at the equivalence point? What's the only thing we have? AC minus, right? And let's look at the dot, the final dot, the fifth dot. What's the only thing we have at that point? Do we have any? We have AC, don't we? AC minus. But don't we also have OH minus?
Yes.
So can you write AC minus and OH minus up there? And circle OH minus, because OH minus is the only thing we really care about. Are you with me?
Yeah.
So this is a typical problem. Oh, by the way, put your finger on the pH equals pK at the third dot on the graph. Third dot on the graph. On the actual graph, the third dot. Okay. Do you see how the graph kind of evens out and the pH doesn't change for a long period of time? Because that's called a buffer region. Because don't we have both the acid and the conjugate base all along that line? So essentially, actually, let's do it on top. So kind of do it from, see where the line appears. Put a line up. Yeah, perfect. That's the buffer region. And why is it a buffer region? Because we have both the HAC and the AC minus. Are you with me?
So I'm not really understanding like the difference between titration and buffers.
They're the same.
Oh.
Titrations become a buffer, except they start off with one part of the buffer.
Okay.
So literally, I'm glad you brought this up. Literally, titrations are identical to buffers, except with a buffer, you start off with an acid and a conjugate base, and you throw a big dog in. With a titration, you throw it in, and the first step, you can't Henderson-Hasselbalch because you're only throwing it into an acid, not an acid and its conjugate base.
So this
Everything else is exact. Like this problem we did right here, you could do every single step on a buffer as well. It would be exactly the same steps. So if you can do a buffer, you can do every titration. Where it gets a little bit sketch is when we have to actually draw curves. That becomes a little bit more problematic for us.
are all the curves gonna look like that?
Only if they're a weak acid being titrated by a strong base.
What about the opposite?
Okay, strong acid titrating a weak base, it's going to be the same exact graph, but flipped upside down.
So like.
So let's draw it next to it just so we can show the similar.
Like
Yep, exactly like that.
End.
Except you went. No, it's not like that. So start up above and draw an arrow down. So draw a little arrow down, like a little. Nope, you're starting with a straight line down. Start with a. So see how, look at our graph down below on to the right. Look at the right. So see how we start off at the zero. Start at the 0 point. I'll start off at the first dot. See how we shoot up and then even off? So when we go the other way, we're going to shoot down and then even off.
Oh, so like.
Shoot down.
Like that?
Well, you still started going sideways at the top. At the top, you go straight down. In fact, let me see if I can find a graph to show you. So, nope.
You start.
Okay, so do me a favor. Make an L shape, and I'm gonna help you draw it. Okay, make an L shape, an L graph. So make your line. Okay. All right. Now put your dot on the actual line near the top. So on the y-axis, put a dot near the top. Near the top. Okay. Now what I want you to do is I want you to draw a line down on about a 45-degree angle. That's right. Okay, not too long. So make the line about half an inch. A little bit shorter, but like right there. Okay. Actually, a little bit longer now. So now I think about it. And you did a 90-degree angle. Let's do a 45-degree angle to the y-axis. So make your angle smaller between the y-axis. So bring it in towards the line farther. So straight, a little bit straighter down. Yes. Okay. Perfect. Okay. Then you're going to shoot straight. Then you're going to even out across. All the way across, like all the way across, until you're ready to go down, and then you're going to shoot down. Okay, but look, see the graph that we did up above. So imagine you look at my hand right now. Let's say the graph's like this. Take the entire graph and flip it like this. So we're taking that entire S shape right here, and we're just going to flip it exactly over so that see how it starts off shooting up and then evens out. It's going to shoot down and even out, and then you see how it drops down. Goes up. We're going to drop down the same amount.
Okay.
The bottom graph, right? The bottom one should be an exact mirror of the other. So if we took the bottom graph and folded it up on the top graph, it would be exactly the same.
Oh.
Does that kind of make sense to everyone?
Like doing the work, like I understand the graph now, but doing the work, it would be exactly the same, except like would it give you, instead of OH minus, it would give you
H plus.
H plus, and then like,
and instead of a hack, it would be AC minus.
And then you would subtract by
same things exactly the same steps all the way through. In fact, do me a quick favor here. Take a look at in your textbook do they even do a titration of a weak base? They of course don't. Oh, they do. Take a look at page 740. Page 740, and I don't want to do the entire titration, but I just want to show you how it sets up. So can you erase or erase everything in the middle of the board here? Oh man, I should have told you to keep that because I wanted to compare the two of them, but it doesn't really matter. So erase to the left, everything up to the left. Yeah, just erase all that. Okay. So in this thing here, we're going to do this. We're going to titrate 100 milliliters of 0.5 molar, 100 milliliters of 0.05, 100 milliliters of 0.05 molar NH3
Wait, 0.05?
0.050 molar NH3 with 0.1 molar HCl. Okay. Now, and by the way, in this case here, the KB, I don't know what, can someone, they don't give me the KB in this problem. Can someone do me a favor? In your packet, I gave you a bunch of a work sheet that says KAs and KBs. Can you guys find that for me? I'm sorry. Online in the folder, I've given you KAs and KBs. Let me see if I can find it here as well. Can someone look up the KB for NH3?
KB NH3. Cody, you have like,
KB is 1.8 times 10 to the negative 5.
oh,
Okay. So now watch. If we were to do the same thing and ask you to graph the same way, we'd have to start off first, and we have to figure out what the pH was before we started the reaction.
Yeah.
Now, understand something here. Isn't this a base that we're dealing with to start off with?
Yeah.
So when we have to do a KB ice problem,
Yeah.
let's do it together. Let's all do it together. Just, I was going to teach you something else, but let's just do this because it'll give you a good sense of this. So let's write NH3 plus H2O. Is the NH4 plus OH minus.
Yeah, so it's just take that.
Right?
NH4 plus.
Oh,
Is that a 4 down below or? Okay, so hold on. In case you're wondering which way to go here, NH3, put your finger on NH3, please. Okay, NH3 is a base. What do bases want to do? Gain or lose hydrogens? They want to gain hydrogens, right? So if it pulls an extra hydrogen on, it's going to become NH4 plus because H is a plus, right? So now we're going to just have an ice problem. So let's do the ice problem for it. Didn't I give you the concentration of 0.05?
yeah.
You know what? I don't want to do 0.05. Let's make it 0.5. I want to make it bigger. This is, I want to make sure you can do the 5% rule, okay? Let's do 0.5 molar.
Does anyone have it?
I don't have any of these because we're going off script. We're not doing the actual problems.
3 times 10 to the negative third. I was
3 times 10 to the negative what?
3.
Okay, so that's our OH minus concentration, right? So if we want to get the pH, when we have to then take the negative log of that and subtract it from 14.
POH is 2.52. And 11.48.
Okay, you got the pH.
Okay, so let's start another graph below where we did the other graph, just so we can do a kind of comparison. Same exact graph, exactly. Do 40, do 14 down to 0. So our 0 mark want to be 11.48. So on the actual y-axis, 11.48.
Could we just do a graph with pH on the side instead of pH?
I couldn't hear him.
Could we just do the graph with pOH on the side instead of pH?
You could, but then the graph would be going up.
It would look like this, but
It'd be exactly like that. Literally, the graph would be exactly like that. So, but we're always going to do pH. So now, watch. Let's do the first scenario here. Let's go. Let's go 50 milliliters of 0.1 molar. Now, as soon as we add this up here, can you go in the upper right-hand corner? Can you write the big dog equation, please?
up here.
Yep.
Where?
Can you write H plus NH3 goes to straight arrow goes to NH4 plus. Does everyone see how that's the big dog in this case? Because isn't it HCl is the big dog attacking the NH3? And can you do me a favor? Can you put like a little arrow through the Cl? Because do we care about the Cl portion of the HCl?
No.
No, we don't. So in this case here, that's my big dog equation, right? Now, what we do now is just take care of everything in terms of millimoles. So don't we have, if I give you 100 millimoles of 0.1, wouldn't that give you 1 millimole?
Oh, wait.
I'm sorry. What did I tell you that I was giving you originally?
Give me 100 milliliters of 5 0.5.
Sorry. Let's start off here. Let's first of all figure out the millimoles of the NH3. Wouldn't that be 0.5 times 100? Wouldn't that be 50 millimoles? Right? And then I want to add in 5 millimoles. So that would be 50 milliliters of 0.1, if I'm not mistaken. I want to add in 5 millimoles. So that would be 50 milliliters times 0.1. Wouldn't that be 5? Look down at A. No, you're right. You're perfectly right there. Sorry, my bad. So for NH3, do you see how we're multiplying 0.5 by 50 by 100? And then here we're multiplying 50. Can you on the left-hand margin, can you write M times V equals N? Okay, so all we're doing is multiplying the molarity times the volume to get to our moles or millimoles. So we have 5 millimoles and we have 50 millimoles. And don't we have 0 of the NH4 plus to begin with? Let's do ICF. The only reason I'm saying F is because it's not equilibrium. So when we have what then? We'd have 0 of the C when we have minus 5 and when we have 5. So don't we have right now both an acid and a conjugate base?
Yeah.
And if we divided it by the overall volume, couldn't we then Henderson-Hasselbalch it to get a value?
Would it be 150 milliliters?
Yep.
Wait. Is it P?
Wait, could you do P?
So now watch. So we still can do the same. Don't we have an acid and a conjugate base? So we can still use the pH equals pKa plus the log of AHA.
So we got KB.
Right. So what does that mean we have to do with the Kb? Convert it to Ka, right?
That was like 5.6 times 10 to the negative.
Yeah.
Minus and plus.
How did you get the Ka?
Ka, we divided the KW by the KB.
Wait,
Okay, good. I just wanted to make sure everyone sees where we got that.
These two.
yeah, but which is which?
This one's the acid, this one's the base. So you put this on top. Oh yeah, class is ending like really soon.
Okay, let's just finish this problem then.
Alright, so go.
Negative log.
What? Oh, that should be long.
Log. Oh.
5.6 times 10 to the negative 10.
Then 8.3.
pH is 8.3.
Okay, your homework is chapter 15, 55 through 60, and I'm putting that online.
Okay. I don't know where you got this part. I think it's from that room. Or that room. Which one? Do you have the long one? Yeah, it's that teacher's.
Bye.
Bye.
Okay,
Bye.
hey, so real quick, make sure that you have your charges next time ready to go, yeah? So I want everyone to have their own computer, and then the link will be on the portal page for you guys to do it. Thank you so much, by the way. You did a great job on the board.
Do better.
Thank you so much. Take care.